Okay, so we'll get started. So we're starting with this question about derivatives, and I'm giving you the graph of a function, and I'm asking you, what does the graph of the derivative look like? So last week, we learned what a derivative is. We did this whole game with the secant lines and the tangent line and limits. The video from Monday's class was also all about that. So you should kind of roughly know what a derivative function is. Today, we're going to finish up learning what it is. And then after today, we're going to learn how to calculate them really well. So of course, knowing what it is, we did some calculations. We calculated the function x squared. We got its derivative, stuff like that. But any questions or comments overall about this kind of stuff before we get started? OK. And so once again, that video on Monday that I posted has 3 examples, like going into detail. How do you do the derivative of x squared? How do you do the derivative of square root of x? How do you do the derivative of 1 over x in a lot of detail with pictures and graphs and like doing all the steps with the limits and everything. So if you're a little confused, you can check out that video, and hopefully it will help you. But OK, let's see what you guys think. So what does the derivative look like? Does it look like this green function, this blue function, this red function, or this purple function? Those are your 4 options. And people chose which one? I guess we're going to find out. People chose, OK, so 57 people answered. We got a 17, 16, 13, 11 split. So pretty split all the way. But the most popular one is this red one, So let's take a look at this function and try to piece together, could that red thing be the derivative? And the way we're going to do it is we're going to use Desmos. Here is the function, and here is this little point that I can drag around and see what the tangent is. And the font is ginormous. Let me see if I can make the font a little smaller. OK, how's that? Better font size? Oh, we have, is this like a, oh, this is cool. You can point this at me. OK, let me change that to this, so we can see it twice. A little better, OK. So we have this little draggy thing that we can drag around, and we learned this whole process of how do you find the slope of the tangent line. And that involves a limit, right? So you actually have to draw the secant line, and then you take the secant line, you shrink it. But at the end of the day, you figure out the slope of the tangent line through this limit trick, and then you can drag this thing around and see what the slope is at any point you want. And that is the derivative function. It tells you the value of the slope of the tangent line at any given point. And you guys think that the slope of the tangent line is this red function that looks like that. It's like a nice like sombrero-looking function. And let's see if this matches the slope of the tangent line. So I'm going to drag around the slope of the tangent line, and then we're going to see if it matches. So right now, the slope of the tangent line is a negative number, because it's going down a little bit. But it's a very small negative number. So does that match the values on the red graph? Small negative number, that would be a negative number just below the axis. Hey, that matches. Look, negative number, small negative number. That's good. And then as you move this over here, the tangent line slope is getting more and more negative. So here, it's become more negative. It's a more negative number than it was before. So before it was negative 0.02, now it's negative 0.15. Does that match what the red function is doing? The red function would have gone down, right? It would have gotten more negative. That matches. That's very good. Matches. All right, here we keep going. Here we keep going. We're getting steeper and steeper and steeper. And now, according to you guys, something interesting is going to happen right at this x value, right here. And the interesting thing is that the red function has its minimum value. This is the minimum of the red function. That's the lowest the red function ever gets. So according to you guys, if it's true that this is the derivative function, that would mean the slope of the tangent line is as steep as it's ever going to get. So it's negative, it's steep, and from now on, it's only going to get less steep. So because the red function went down, 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 it reached its minimum. If it's the derivative function, then that should be the maximum steepness. And then it should start to kind of pull up after that, right? The value of the red function is starting to pull up, so the steepness of the tangent line should also start to pull up. Let's see, does it do that? So here we're at negative 0.48. OK, a little more steep. And we're starting to pull up. So it's pulling up. It is pulling up. And then eventually, it hits 0. So it did start to pull up. And then eventually, it pulled up all the way to 0. And that does exactly match what's going on the red function, because the value of the red function is exactly 0 at 0. So far, pretty good story. It has the small values in the right places. It kind of pulls up at approximately the right place. And it's 0 at the right place. So far, looking good. Most popular answer is looking good. Let's see what happens if we keep going. If we keep going, Now the tangent line is getting positive, 0.5 slope, 0.6 slope. The slope of the tangent line here is positive. The slope of the tangent line is positive. But the red function, that was the most popular answer, has negative values again. The red function is below the axis. The values of the red function are negative. And so this is a very obvious mismatch. There is absolutely no way that the red function can be the right answer because it is negative where the slope of the tangent line is positive. Absolutely cannot work. So the story for all the negative numbers, that worked pretty good. But the story for the positive x values is all wrong. The red function is definitely wrong. So that being said, the red function is definitely wrong. That was the most popular answer. I'm going to let you re-vote. Try to put together this story. You're going to have to do it in your head, I guess. Imagining the tangent line. I guess I can also display it on Desmos while you're thinking. But we're going to re-vote and try to do it again. And feel free to talk to your neighbors. Let's see if we can get more people on just one answer. So I'm going to close this. I'm going to repeat exercise. And we're going to run it one more time. And you'll have 2 minutes to work on it. So there you go. Here it is. Try again. And while you're doing it, I will play a little animation of this thing to get your brain juices flowing. Here we go. So here's the animation. The tangent line slope, what does it look like? And what does that corresponding function look like? So it's open in Math1030. I'll give you, let's say, 1 minute. So we can make sure to get to everything in today's class to try to guess what is the right answer. Yeah, so everybody's order is different, but the colors are the same. So if you should say, I think it's the blue one, or I think it's the green one, or I think it's the purple one. That should work. Okay, so I'm going to close the voting. Hopefully between this animation and thinking about it, you guys came up with an answer. 50 votes. Some people didn't vote this time. I'm going to close it. You got to vote. 3, 2, 1. Okay, so red, only 3 people didn't get the memo that red is the wrong answer. 30 people are in blue. What about the other ones? 30 people are in blue. 12 people are in purple. Purple is kind of wrong for a very similar reason that red was wrong. So purple is not right. Purple is this one. Nope, that's red. Purple is this one. This purple function is always positive. So if you think the purple function is the right answer, that would mean the tangent line is always positive slope going up. But we saw that the purple slope can't be right because the slope of the tangent line is negative here. So the purple is not right. And the most common answer was blue. Blue looks like this. Blue is the correct answer. Let's see why blue is the correct answer. Blue is the correct answer. It matches the story perfectly. First of all, it's negative for all the parts over here, like we said. And if you look at the peak steepness, according to the blue function, the peak steepness happens right here at negative 0.649, something like that. So according to the blue function, that is the steepest it will ever get, and then it's going to start to pull up after that, right? The value of the slope pulls up and goes all the way to 0 by the time you get here. Let's see, does it do that? So 6.47, 0.64, and then it pulls up until you're at slope 0. That matches perfectly with the function. That blue curve is exactly telling you the value of the slope of the tangent line. On the other side, it's a mirror image, and it's doing the right thing. It starts at a slope of 0, and then it pulls up to a peak steepness right around here. The peak steepness happens right here at 0.577. So right around there is the peak steepness, and then it's going to start to mellow out and go down. So let's see it go down, down, down. And it's always positive, but how positive it is getting smaller and smaller. That's because the blue function is always above the axis, but getting closer to 0. So the blue function is always a little bit positive. The original function in black is always sloped very slightly up. So this matches perfectly. This is the right answer. So congratulations to the 30 or so people who got it right. Great job. Okay, I think I forgot to put in which ones are wrong and right. So it says they're all right, but believe me, only the blue one is right, the other ones are wrong. Okay, let's fill this in our notebook. This function occurs on page 445 in the notebook. It's the exact example we just did. And in the notebook, they also tell you the formula for the function, but that is completely irrelevant for what we're doing right now. You just need to know what the picture looks like. And again, I'm going to highlight the elements we use to find the right answer. One element is increasing versus decreasing. So we said this function is decreasing all the way here. So it's decreasing here. I'm going to write dec for decreasing here. So again, it's very important when you're doing with this stuff to really separate in your mind the original function, the original function f. That is this guy up here, f, and that is drawn in black, okay, versus the derivative function, which we'll do down here in blue, the derivative. So don't mix up these two functions, they're different functions. So when the original function is decreasing, it's going down. That means if you were going to draw a tangent line anywhere on the original function, that tangent line would be pointing down. And if it's pointing down, it has a negative slope. So where the original function is decreasing, the derivative function is negative. So it's somewhere here. Here, the derivative function is negative. Derivative function, this blue function, is negative. It has a negative value. Where the original function is decreasing, the derivative function is negative. Similarly, on the other side, where the derivative function is, where the original function, excuse me, I misspoke, where the original function is increasing, to the original is increasing here. Where the original function is increasing when it's going up, the tangent line to the original function is pointing up. It has a positive slope, and therefore the value of the derivative function is positive. So the derivative function, the deriv function is positive. So increasing and decreasing translate into positive and negative for the derivative function. So we know the derivative function is going to live in this green zone and this yellow zone. It's impossible for the derivative function to have values here, right? Or values here. And that is how we caught the red function and the purple function as being the wrong answer. They were not positive and negative in the right places. What other things can we observe? Well, there's one special point, which is where there is a horizontal tangent. There's a horizontal tangent. And you can see that right there at this like peak over here. There's a horizontal tangent. A horizontal tangent means the slope is 0, and that means the value of the derivative function is 0. The value of f prime equals 0 here. The value of the derivative function is 0. Other than that, the other feature that you can use is the sort of peak steepness thing. And we said there were these 2 points. One was approximately here, and one was approximately here. These are the 2 points that I call the peak steepness. Peak steepness. And this is the peak steepness for positive, where you're as steep as you're ever going to get going up. And this one was the peak steepness for negative. The peak steepness for negative. Steepness for negative. And that is as steep as you're going to be ever going down. And those translate to the minimum and the maximum value of the derivative function, right? The tangent line will never be smaller than, more negative than when it is here, and the tangent line will never be sloped more positively than it is there. So those are the kind of the min and the max. And then the other thing we saw is that the slope is going to 0 here, right? The slope is 0 near the ends. So if I connect the dots, what is going to be? It's some function that looks like this. It's going down, it goes through this, and then up, and then kind of symmetric like that. And it's getting really close to 0 because the tangent lines are getting closer and closer to flat on either end. But that is the picture of what the derivative function looks like based on the picture that we have there. Are there any questions or comments about that? I know it's a lot of different facets all coming together. Okay, a lot of people got the question right, which I think is good. Okay. Okay, let's do another one. And in this one, before we do another one, let me comment that some of them have already been done in the video from Monday. So this f of x equals square root of x, the derivative looks like this, and we even got the formula f prime of x is 1 over 2 square root of x. And if you want to see why it looks like that, that is all in the video that was posted on Monday. So this is all from video. I'll leave it up for those of you who want to quickly copy down what it looks like. But I do encourage you to go watch the video. Okay. Okay. Here is another one. This is some cubic equation. Let's repeat what we just did to draw a picture of the derivative. And again, don't mix up the original function f with the derivative function f prime. Think of them as two separate things. And information in one translates into information in the other, but it's not like the exact same thing. And the first thing that we said is increasing and decreasing. This function f is increasing from here to here, and then it turns around and goes decreasing from here to here, and then turns around one more time to increase from there to there. So that goes increasing, then decreasing, then increasing. So it's increasing, then it's decreasing, and then it's increasing again. And how does this translate into the function f prime? When it's increasing, the tangent line is positive, the value of the derivative is positive. So what does it look like? It will be some positive value up until this special point, right? So positive, positive, and then it's going to be negative where the original function is decreasing up until here, negative, and then it's going to be positive again, positive again. So increasing and decreasing translate into positive and negative. The original function was increasing and decreasing, and that tells us where the derivative function is positive and negative. So that's the first thing. The second thing we said are the horizontal tangents. The horizontal tangents here and here. And so these are the horizontal tangents. Horizontal tangents. And at a horizontal tangent, the value of the slope of the tangent line is 0. It's a flat line. So that means the value of the derivative function is 0 at those 2 points. Where the function is switching from increasing to decreasing, it has a horizontal tangent, and the value of the derivative is 0. The other thing we drew are the peak steepness moments. And I think the peak negative steepness happens here. This is peak negative steepness, peak negative steep, somewhere in the middle, right? It sort of gets steeper, 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 and then it turns around and gets flat again. And that will correspond to some most negative value down here. So this is the most negative value. Negative value there. What about peak steepness for positive? Well, this function, it sort of gets steeper and steeper the further you get. So the positive peak steepness moments are sort of like up here and down here. It just gets more and more steep the further you get. And that is saying that the function is kind of going up to infinity. It's going to look something like this. It's going to have large values, large positive values here and here. I guess here, let me draw them in the right x places. Here and here. It has large positive values here, large positive values. And it has large positive values because the slope on the original function is very steep and positive. Okay, so those are the dots. Now we can connect the dots, and it's going to look like this. It's a function that starts out very positive, hits 0, then it's negative for a while, it hits its most negative value, turns around, hits 0, and then it goes up to a positive value. And it's going to go up forever like that. So that is my picture of the derivative function, just all using paper and my intuition. In a second, I'm going to check it on Desmos and see if it worked out correctly. But this is a really good place to stop for questions or comments, because you're going to have to do this kind of thing on the final exam on your homework. So questions or comments about this one? OK, let's check in Desmos and see if Desmos agrees with my paper. So let me go into Desmos. And I think it's this one. OK, yeah, here is the function. We use the formula that they gave us to get this function. And let me zoom in a bit, make it a little more interesting. So, OK, there, something like that. Does that match what's in the notes? Let's freeze the notes. And then we will see. Let me freeze this. Freeze that. OK, and there we go. So is it matching the function? Yeah, OK, so that blue function is like the original function. Let's make it, to keep things consistent, let's make it black. Black, OK, there we go. And the point is we can slide this thing around to see the slope of the tangent line, and we can sort of recreate all the logic I did in my head. We can do it numerically in Desmos, right? So is it true that the slope of the tangent line is 0 at these two peaks? Well, Not exactly, but I think it's just I got to slide it closer. It's very close to 0. If I could slide it perfectly, it would probably be exactly 0. And same thing down here, it's 0. Is there this peak steepness moment in between? I said there's this peak negative steepness where you go super negative. It's like you're going down a roller coaster, and this is your maximum angle, and then you start to pull up and go like that. That happens somewhere in the middle. That's great. And is it very positive at these ends? Yeah, big positive number, I guess like that. 6, 6.9, it's just getting more and more positive the further out you get. So that seems to work quite well. And we can ask Desmos, please just plot a function whose value is the slope of that tangent line everywhere. And if we do that, it will look like this. That is the value of the slope of the tangent line in purple, and it matches very positive over here, zooms down to 0, it hits 0 right when we have this horizontal tangent on the original function, peak steepness moment happening right about there, and then turning around to hit 0 again at the horizontal tangent here again, and then going off to very steep once again. So that matches pretty well. Does that purple function that Desmos calculated match what I drew? Yeah, they look pretty good. I'm pretty happy with that. Any questions or comments about this idea of the derivative function? This is doing a derivative visually. Okay, let's do one more example then. And this example is going to be a bit different. Let me just make sure. This example is going to be several pages earlier. It's the function absolute value of x on page 442. And here is the original function. It looks like a v, right? We've seen this function a few times, the absolute value function. And the question is, what does the derivative function look like? And I want you guys to do this one visually. In the notes, they also do it with algebra. I'm going to skip the algebra. The picture is already good enough to understand this question. We're going to do it just with the picture. So take 1 minute or 2 minutes and try to do it. Try to do the derivative. Try to graph what it looks like. Graph. Okay, I'll give you guys 2 minutes to try it. There's no mathematize or anything, but just try it out, and then we'll go over the answer. Okay, let's take this one up and draw a picture of the derivative. So the first thing I guess you should have done, or that maybe you would have thought of, is this increasing, decreasing thing. And it's very easy to see the function is decreasing on this side and increasing on this side. I'll wait a second for people to stop talking. All right, thanks. So it's decreasing and then increasing. It's decreasing over here, and it's increasing over here. So on the negative x values, it's decreasing. On the positive x values, it's increasing. And that means the derivative function will be a negative function. It'll have negative values over here, negative values. And on the other side, it will have positive values, right? So increasing and decreasing translate into positive and negative values. Not nec, but negative. Okay. So that's the first thing. The derivative function is going to be negative for x less than 0 and positive for x bigger than 0. Put your hand up if you have negative and positive correct on your graph. All right, lots of people. That's great. The next thing to think about is how is the steepness changing as you move? So you could kind of imagine you're sitting here on the roller coaster and you're going down, but are you going down faster and faster and faster, or are you kind of like slowing down and like pulling up? And in this situation, something very interesting happens is that neither is happening. If you draw the slope at any point, it's always the exact same steepness no matter where you are. So that blue dot has the same steepness as that purple dot, which has the same steepness as that pink dot. The steepness of the tangent line is always the same on this function because it's a perfectly straight line. And so the value of the derivative is always the same number. It's just some constant function. It goes like this. If you connect the dots just on this side, it's always just some negative number. This, if I was a better drawer, it would be a perfectly straight line. It's always the same negative value. It's whatever the slope of that line is. If you have a line, whatever the slope of the line is will be the value of the derivative. It turns out this slope is -1. This is -1. You didn't have to do -1 to draw the picture, but the slope here is -1, and that's just a fact. Okay. You can see that from the piecewise version of absolute value of x. That was where the negative values. What about the positive values? Well, the same idea happens in reverse, which is you have some fixed positive amount, and that is just the slope of the positive values over here. So it's always that same amount, and it's not changing. It's not getting more steep. It's not getting less steep. It doesn't have a peak steepness moment. It's just always the same thing. It's always a constant, and in this case, the constant is +1, the slope of the line. So it's -1 over there. It's +1 over there. What happens in the middle? This is the really exciting question that you have to answer. We've done all the work for x less than 0. We've done all the work for x bigger than 0. What happens exactly at x equals 0? And if you go through all of the stuff we did with the secant line and limits, that will answer the question definitively. The tangent line, the ancient Greeks were confused by it because you could say there's more than one tangent line here, that kind of thing. But for us, we have a very specific definition. You take the secant lines, you take their limit, whatever the value of the limit is, that is what we want, right? This f prime means the limit of the secant lines. It's defined by a limit. And fortunately for us, Desmos will do the limit for us. So let's go into Desmos and ask Desmos, please tell us what the value of the limit is. And that I did on this graph over here. So here is the function, and let me get rid of this line. I think this line is confusing, and let's get rid of this point of interest, and let's get rid of where it says original function. Okay, so we have this dot. The absolute value function is plotted in blue, and I have this dotted line that tells me the tangent slope. And you can see it's always -1 over here. It's always -1 over here. It's always +1 over here. No matter where you slide it, it's always +1, and it's always -1. So we've done that so far. But the question is, what happens exactly at x equals 0? And Desmos will answer it for us by just putting the point exactly at 0 and seeing what happens. Okay, I got to get it exactly at 0. The tangent slope is equal to undefined. At 0, the function is undefined. That is the right thing that is happening. So you should draw on your graph, you should draw big fat open dots. Undefined at x equals 0. So this is a big important new concept. The slope of the tangent line is not defined at 0. The derivative is not defined at 0. And why is it not defined? Maybe even more specifically. So first of all, make sure you understand that it's not defined. But the reason is because if you do this whole game with the secant line, you do not get an answer. Let me make the secants go from, actually I can just zoom in. I want to go this way. Let's zoom in. Okay, so here's the secant line. And here, the secant line, the slope is -1. Here it's -1. And the secant lines are always that orange line pointing down. But over here, the secant line is always +1. So what is the limit of the secant lines? The limit does not exist. So on this side it's positive 1, on this side it's negative 1. It is not getting close to any one value, and that is the reason the tangent slope is undefined. It's a limit that doesn't exist because one side is positive 1 and one side is negative 1. And you can see that almost in our picture over here. On one side it's positive 1, on the other side it's negative 1, right at x equals 0. It doesn't exist because the limit doesn't exist. The limit does not exist. And if you want to be even more specific, you could tell me which limit. It's the limit as h goes to 0 of f of 0 plus h minus f of 0 divided by h. That limit does not exist. That limit is going to tell you the slope of the tangent line, and that limit does not exist here because on one side it's plus 1, on one side it's negative 1. So that is the picture proof, and we have discovered this thing that if you have a corner, the limit does not exist at a corner. In the notes, they also do this with algebra. I'm going to skip doing it with algebra. I think the picture proof is perfectly fine. But if you want, in the notes, they do this whole proof of why the limit doesn't exist. And I think that problem was actually, this was a problem that was on the practice midterm, was explaining a limit that doesn't exist. So I'll do that in an extra video, but you don't need to know the algebra. Just make sure you know the picture. OK, are there questions about this idea that the derivative doesn't exist at a corner, like in the absolute value function? So this idea is explained later on in the notes as well. So if you go forward a few pages, let me freeze here. But if you go forward all the way down here, they have the three cases where the derivative does not exist. And we just did the middle case. This is the corner. If you have a corner, the derivative does not exist. The derivative function will have a jump at that point, just like for the absolute value function. The other ways you can not have a derivative, you can have a situation where the function jumps. And in this case, I'm going to say this is a jump. So if the function has a jump, the derivative also won't exist. Once again, the secant lines will not converge. And finally, you can have what is called a vertical tangent. A vertical tangent. At a vertical tangent, you might say the value of the slope is infinity there. But because infinity is not a number, the function is just not defined there. The function will just blow up to plus infinity at this point, and therefore it won't be defined. So these are the three cases where the derivative does not exist. OK. Any questions or comments about this one? All right, we have one more mathematized question to do, and it's a fun, easy one, because we are done with this section, and we are moving on. Next class, we are going to be moving on to this section called differentiation formulas. And we worked so hard in the last section to try to do things like the derivative of x squared that took us basically a whole class to understand. And in this section, 11.5 on differentiation formulas, we're really going to hit the gas and go fast and do a whole bunch of derivatives. Look at all these derivatives we're going to do. And the reason we're going to go so fast is because we're not going to use the limit definition. We're going to use other formulas for doing derivatives. But before we do that, I want you guys to understand why we are doing it the way we're doing it. Why did we spend so much time doing it with limits if there's a fast way, in quotes, to do it? And I came up with a fun analogy involving cars. Analogy with cars. I want you guys to answer the question about cars, and then we'll take it up next class and use that as the starting point for when we do more stuff. So here is the question about cars. Suppose you are designing a course called Cars 1030 for first-year university students who should know the basics about cars, but are not car majors. Which topics should be included in the course? And for this, you got to pretend that you don't know anything about cars from real life. It's all the stuff you're learning in the course. And there's three options. There's how the engine works, how driving the car works, what route you would take to get from Toronto to Montreal. And I want you to select all the ones you would include in the course. So maybe you want to include all three. That would be a valid thing. What should we include in the course? Cars 1030. And next class, I'm going to explain what this has to do with derivatives. It's an analogy for why we're doing things the way we're doing. But once you do that, you can go home, and I'll see you guys on Friday.